everyone. Here we are for the first video lecture for Chapter 14. Chapter 14 introduces the topic of statistical inference, and what we're actually going to be talking about here is something that's really useful in terms of analyzing data that you collect from an experiment, or polling data from an election or election campaigns, or any number of things. And so what we're doing here basically is looking at a sample average and trying to understand or qualify that sample average in terms of how good of an estimate of the true population average it is. Okay, so we've talked about taking sample averages before with regard to sampling distributions and all that sort of thing, but with this chapter we're going to look at the sample average and say, okay, how good of an estimate of the true population mean is this sample average? Okay. All right. So we're going to talk about uncertainty and confidence. In particular, we're going to focus on confidence intervals, which are really useful tools. Okay. And then later on, we'll get into what are called tests of significance and null and alternative hypotheses. And all of this, obviously has to do with statistical inference. Okay. All right. So let's say, for example, that, again, we're looking at human height. It's an often used example here. So we have a population, and we know beforehand that the heights are normally distributed. And in this case, we have a certain mean and a certain standard deviation in that population. So let's say we take a sample of 217 people, measure their heights, and average those heights. And we get a mean sample average, note X bar, so it's a sample, right? A mean sample average of 132.5, say, centimeters. Okay, take a second sample, 217 people, different people than the first sample, average that, you get a mean of 134.2. Third sample, we get a mean of 131.8. So notice that these means are not the same. They will almost never be the same except by pure chance alone. Okay, so all these different means will be different. And again, we plot those on a frequency distribution, we get what's called the sampling distribution, right? How the sample means fall out. Okay, another thing about this is that the more of these samples we take and the more than we plot on our frequency distribution, and the larger those samples are, the closer the mean of that frequency distribution will be to the true population mean. Okay, all right. Remember, we've also talked about the empirical rule, 68, 95, 997 rule, which says that if you go out plus or minus one standard deviation, and so notice here on our sampling distribution that our standard deviation is 0.7. If you go out plus 1 and minus 1, you've encompassed 68% of that curve. You go out 2, and that's what we have here, plus 1.4, minus 1.4. That is 2 standard deviations. Now you've got 95% of the curve. If you go out 3, then you've got 99.7% of the curve, okay? And also, just to clarify how we got the sampling distribution standard deviation of 0.7, well, our population standard deviation is 10. And remember that the sampling distribution standard deviation is the population standard deviation divided by the square root of n. So you take 10 and divide it by the square root of 217 for sample size, and you get 0.7. That's your sampling distribution standard deviation. Okay, so let's look at how we can use what we learned about sampling distributions in the last chapter. So remember, we have a population distribution here, okay? And again, that curve is defined by its mean, population mean, and the population standard deviation, right? Now, the sampling distribution should have the same mean as the population distribution, but its standard deviation will be smaller because, again, we calculate that, sorry, it's missing, we calculate that as sigma divided by the square root of n, okay? Again, that gives us a more narrow distribution for our sampling distribution. Now, if the population is normally distributed, normally distributed and defined by a certain population mean and standard deviation, the sampling distribution will also be normally distributed, defined by the same mean, but now a standard deviation divided by the square root of n. Okay. If our population is not normally distributed, though, okay, the sampling distribution will be approximately normal if our sample sizes are large enough. That was a key point that we made in the last chapter. And again, this is one very important reason for taking the largest samples we possibly can. So we have a sampling distribution, let's say that's normally distributed based on a population distribution. Basically, in statistical inference, we take one random sample of a given size and we rely on this known relationship between the sampling distribution and the population distribution to infer certain things about that sample average. Okay, there's a relationship between our our sampling distribution and our population distribution, and we can use that to our advantage to infer certain things about a sample mean and how it relates to the population mean. Remember, we're taking a sample because we want to understand something about the population mean that in most cases we can't know directly. Okay, so what we do here is we calculate what's called a confidence interval. Okay, a confidence interval. Now, a confidence interval basically is how we qualify how good our sample mean is as an estimate of the population mean. All right, what you're seeing here is a screenshot from a statistical applet simulation, and this is on Canvas. Okay, this is the confidence interval applet that you can find on Canvas with the chapter 14 materials. Okay, so what we have here again is our population distribution, and in red you see our sampling distribution. They both have the same mean, right? But again, different standard deviation as we've talked about. Let's say we take one sample, and let's say that sample is size 20, right? We have 20 data points in that sample. You see how they fall out on the x-axis of the population distribution. If we average those 20 data points, we get that black circle right there. That's our average of those 20. It's pretty close to that green line, which is the actual population mean, isn't it? Okay, but we don't know from the start how close that sample mean is to the true population mean because we don't know what the true population mean is, do we? No, that's the whole reason we're sampling, after all. So what we need to do is find some way to qualify that and get an estimate or a probability for how close it is to that true population mean. And that's what our confidence interval tells us. This horizontal bar that you see here, extending the same distance to the right and to the left of our sample mean, that whole distance from this point to this point, that's our confidence interval. Notice that in this case, that green line, the true population mean, falls within that confidence interval. It's not over here on this side, it's actually between these two extreme values of our interval. All right, now what we've done here on this screenshot with this applet is we've set our confidence level at 95%. That means we want to be 95% confident in that sample average as an estimate of our true population mean. Okay, so that's one sample. Here you see that one sample, this first one. Now what if you take a different random sample? You get a sample mean here, but notice that it also includes the true population mean. The green line is within the confidence interval for that sample. That's the case for our third sample, and our fourth, and our fifth, and our sixth, and so on down the line. All of these encompass or include the population mean in the interval until we get to this one. This sample, the confidence interval lies just outside the mean, or I should say the mean, population mean lies just outside the left boundary of our confidence interval. So for that one sample, our confidence interval did not include the true population mean. All right, so we have what, I think 25 samples here, 25 samples, okay, oops, sorry about that. And we see that one of them did not encompass the true population mean. That means that 96% of them did. 24 of them hit it, one of them did not. So that's a 96% hit rate. Well, we set our confidence interval at 95%. That explains why this number is nearly 95%. Okay, we want to be 95% confidence that any given sample mean contains our true population mean. Does that mean they always will? No. On average, 5% of the time they won't. If you set your confidence interval at 99%, then 99% of samples would include the true population mean within their confidence interval. 1% on average would not. 90% confidence interval. 10% on average of your samples would not include the true population mean within their interval, okay? All right, so we take a random sample, we can compute the sample mean, and an interval of size plus or minus 2 times the sample distribution standard deviation around the mean. That's effectively what a confidence interval is, a 95% confidence interval is. Remember, 2 standard deviations out from the mean encompasses 95% of our curve, right? Okay, so, and typically 95% is sort of the standard in statistics. We typically try to at least use that. You could try and be more sure by setting the bar higher and selecting a 99% confidence interval, but typically it's not necessary. Usually 95% is good enough. 90% you sometimes see, but generally speaking, that's setting the bar too low. We're not sure enough with that. Okay, we'll see more about that idea here in a little bit. Okay, so based on our empirical rule here, okay, we can expect that 95% of the time, our intervals computed with this method will capture our population mean. That's if we calculate a 95% confidence interval. Okay, so more about confidence intervals. Again, these are a range of values with an associated probability, or a confidence level that we define as C. Now you can set that confidence level to whatever you like. Like I said, most often we set it at 95%. The confidence level is a probability that measures or quantifies the chance that the interval contains the unknown population parameter. And typically this unknown population parameter is our population mean that we're trying to estimate with the sample mean, okay? All right, so we have all these different samples like we looked at before for human height. And if we do 100 of them and we set our confidence level at 95%, then 95% of these intervals would include or contain or capture, as they say, the true population mean, okay? We would have 95% confidence that the mean falls within the interval that we have calculated. All right, so confidence intervals are related to margin of error, and maybe margin of error is something you've heard more about. If you've been watching election polls, you note that whenever they show percentages for Biden or Trump or Cunningham and Tillis in North Carolina, whatever, they always show a margin of error, okay? Now, the margin of error is important because it shows you how much variation there is in the estimate of those percentages, of those probabilities, right? Okay, so with a margin of error, what we have is basically half of the confidence interval. So let's say you have a confidence interval like this, right? And you've got your sample mean in the middle of that, all right? 1/2 of this would be your margin of error, or MOE as we call it, okay? So 2 times the margin of error is your entire confidence interval. And typically there's 2 ways to cite or state or express a confidence interval. You can do it as a center, so a mean, plus or minus the margin of error. So sample mean plus or minus the margin of error, that's very common. Or less commonly, you'll see it actually expressed as an interval, where you have your population mean within some interval. The interval would be your sample mean minus the margin of error to your sample mean plus the margin of error. That is what you would have sort of right here, for example. This is an interval, a confidence interval, the whole thing that I've drawn here, right? That is your mean minus your margin of error defines this point, and your mean plus the margin of error defines that point. So here you've actually stated it as an interval, whereas here you've stated it as a mean plus or minus the margin of error. And again, the confidence level represents an area of corresponding size under the sampling distribution. Confidence intervals are probabilities. Areas under our curve are probabilities, as I've said countless times this semester, right? So let's say we set our confidence interval at 80%, which is kind of what this figure here looks like. This looks like to be about 80% of our area, okay? So that's our margin of error, right? Our confidence interval, which is 2 times the margin. Well, what about these tails over here that are not included, okay? Well, how you calculate their area is this way. So we have 1 minus 80%. 80% is our probability C. That'd be 20%. Divided by 2, because there are 2 tails, would make this 10%. 1 minus 80%, or 100% minus 80%, 20% divided by 2, 10%, right? That's how you would calculate the area of those tails. Okay, so if you had a 95% confidence interval, and maybe you had the ends of your confidence intervals here, then you'd have 100% minus 90% would be 10%, which would make this 5%, and this also 5%. At 95%, the two tails would be 2.5% each, okay? All right. So let's look at an example. A 95% confidence interval for the mean body temperature in degrees Fahrenheit was computed as 98.1 to 98.4. Okay. And that's based on body temperatures from a sample of 130 people, okay, healthy adults. What is the correct interpretation of this interval? Well, let's read through them all. A, 95% of observations in the sample have body temperatures between 98.1 and 98.4. B, 95% of the individuals in the population should have body temperature between 98.1 and 98.4. Or C, we are 95% confident that the population mean body temperature is a value between 98.1 and 98.4. Well, here's how you figure this out. Confidence intervals are always about averages or means. They are never about individual observations or individuals in a population or a study. They're always about means or averages. So correct answer is C. A 95% confidence interval in this case tells us we are 95% confident that the population mean body temperature is a value between 98.1 and 98.4. That is always how you interpret a confidence interval, okay? Now, what about margin of error? Well, to answer this question, you have to think about the confidence interval. So the confidence interval is 98.4 minus 98.1, which equals 0.3, correct? That's a confidence interval. That's the length of your confidence interval. Margin of error is always half that. So what's our answer? 0.15. That's our margin of error, okay? All right. Now, let's talk about confidence interval for a normal population where the population mean is unknown. That's what we're always assuming here, is that our population mean is unknown, okay? How do we calculate this confidence interval? Well, it's actually quite easy, okay? We've already seen part of the calculation in the last chapter where we looked at z-scores, okay? So when taking a random sample from a normal population with known standard deviation, okay, a level C confidence interval could be 90%, 95, 99, whatever you set it at. A level C confidence interval for the population mean is defined by this expression right here. It's our sample mean plus or minus a z-score multiplied by our sampling distribution standard deviation, which again is always our population standard deviation corrected for the size of our sample. All right, so that's a mean plus or minus the margin of error. This right here, your z-score times your sampling distribution standard deviation, this part is how you calculate the margin of error, and then 2 times the margin of error is your entire confidence interval, okay? So let's take a look. We have confidence level, in this example, set at 0.8 or 80%, right? What we need to do is find z-scores that represent the boundaries that encompass 80% of our curve, because we're looking for an 80% probability, okay, that our population mean falls within these two limits. So we need these z-scores, and you see that on this figure they've shown you the z-scores are 1.28. Well, how do we know that? We have to look them up on a table. So in the last chapter we used table B to find z-scores, right? Remember, a z-score is just a way to take either an individual measurement or a sample mean and convert it to a standard deviation. Remember that. That was last chapter. Okay, well now we're going to do the same thing, except we need a different table. We need table C. You see table C right up there, all right? So with table C, we have a lot going on. First of all, at least in terms of where we are in this course, right now, you do not have to worry about these numbers in the body of the table. Those are called t-values or t-statistics. We're going to get to those later, so disregard those now. All you need for now is two rows. You need this top row here that's highlighted in the blue rectangle, and you need this bottom row here also highlighted, okay? So we have our confidence interval or level here. You see we have, 50% all the way up to 99.9%, but again, 95% is most common. And down here we have corresponding z-scores. Okay, so let's take these two rows and condense them and look at it right here. So at 95% confidence, we have a z-score of 1.96. Okay, go back to the previous slide. We were looking at a confidence level of 80%, and they're showing z-scores of 1.28. Why? Well, let's look. 80% confidence, 1.282 is the exact value. There it is. That's where those z-scores came from. But as I said, we're typically using 95% confidence, so we're concerned about this z-score. Remember from the empirical rule that if you go out plus or minus 2 standard deviations, you get about 95% of the area of that curve, right? Well, technically it's not quite 2%, or 2 standard deviations, it's 1.96. We just round it up to 2. So 95% of your curve is defined by plus or minus 1.96 standard deviations, almost 2 standard deviations, okay? So let's look at an example of how we use this. So, density of bacteria in a solution. Measurement equipment has normal distribution with standard deviation of 1 million bacteria per milliliter fluid. All right, we take 3 measurements. Here they are, 24, 29, and 31 million bacteria per mil. That's a sample. That is a sample with sample size of 3, okay? Our mean of those 3 measurements, our mean for that sample is 28 million bacteria per mil. This is asking you to find the 99% and 90% confidence intervals. All right, again, iPad's messing up my formatting here. Let me fill these in real quick. Okay, that's a sigma, not a G. All right, same thing over here, plus or minus sigma. Okay. All right, so let's do the 99% on the left first. So we need to find our z-score right there. We know what our population standard deviation is. It's 1 million. We know what our sample size is. It's 3, all right? So look down here at your table. So this is an abbreviated part of the table, table C. So at 99%, okay, so I kind of wrote over it, 99%, we have a z-score of 2.576, right there, 2.576. So we have a mean of 28 million plus or minus 2.576 times 1 divided by the square root of 3, right? That's this calculation here. Do the math, 28 plus or minus 1.5 million. So that's our margin of error, 1.5 million bacteria per mil. You multiply that by 2, you get the entire 99%, in this case 99% confidence interval. All right. That means that 99% of the time, our population mean will fall within the interval of 26.5 to 29.5 million bacteria per mil. All right, now 90% on the right-hand side. So for 90%, we have a z-score of 1.645. So again, plug in your numbers. 1.645 times 1 over the square root of 3. Again, that's this calculation here. You get 28 plus or minus 0.9 million bacteria per mil. So this is our margin of error. Again, in this case, our 90% confidence interval is going to be 27.1 million to 28.9 million bacteria per mil. Notice that our 90% confidence interval is narrower than our 99% confidence interval. So 99% is a higher bar than 90%, okay? You're less certain with a 90% confidence interval because it's more narrow. You're less certain that your true population mean falls within that area around your sample mean. So here you'd have a sample mean maybe that has a confidence interval that looks something like that. Over here, you'd have a sample mean with a confidence interval, I didn't draw that right, that's much wider, okay? So it's more likely that your population mean is going to fall within that because it's a wider confidence interval, so you have higher confidence in that. Higher confidence intervals are larger, they're wider. Lower confidence intervals that we have less confidence in are more narrow, okay? All right, so we have a link then between our confidence level and our margin of error, like I kind of talked about before. So our margin of error, again, is m equals our z-score. Whoops, sorry, go back. M equals our z-score times our population standard deviation over the square root of n, okay? So higher confidence, C, 95% versus 90%, for example, implies a larger margin of error, and that gives us less precision in our individual measurements in the sample, but higher accuracy in terms of that margin of error, or that confidence level interval, including the true population mean. A lower confidence level, say 90% or 80%, produces a smaller margin of error and therefore a smaller confidence interval. So you have more precision because your sample measurements are closer to each other, more precise, but potentially less accuracy because you're less likely to include your population mean within that smaller confidence interval, okay? So more precision here, but less accuracy. All right, I think that's a good place to stop for this particular video. The next topic is something much more, not really much more complicated, but it goes into a lot more detail, and so this represents a really good stopping point. So we're going to stop here and pick up with the next video on significance test, how we use a confidence interval to gauge really how good our sample average is as an estimator of our true population mean or average.